Hello and welcome back on this channel. Today I want to show how I check this coaxial cable it's coming from my country house. It's been outside for years and I need to check if this cable is still good or not. Uh, it's um, it's not too long, probably I'm not sure, probably 15, for sure between 10 and 20 meters, but we will check the length with the help of the MFJ. And yeah, so as you can see, it has got two PL259 on both sides, which I'm going to replace because these are quite old and probably oxidized, as well as the braid on the connector side. So, but yeah, before replacing those connectors, I'm gonna run some tests to check the condition of it after so many years of being outside. As you can see, it's all dirty, but hopefully I can still use it. And we're going to compare the characteristics that we measure with the with a data sheet of the same type and see how it behaves after so many years of being outside at the weather. So, in order to check this piece of coaxial cable, I'm going to run those few tests in order to measure the characteristic impedance of the cable to see if it's still 50 ohm or close to it. We're going to check the center conductor and the outer shielding resistance and compare it to the datasheet, as well as the attenuation of the cable. Obviously, we're going to measure also the length of this cable. So let's grab the MFJ that I have, this instrument here, and with the help of this we're going to run these tests. So in order to measure the characteristic impedance of this line, which is indicated by Z, we use this formula, the square root of L inductance over C capacitance. And so what we need to measure is just simply the inductance and the capacitance of this length of transmission line. And we're gonna use the MFJ and write the value down here, and then we'll do the math. Very simple. Okay, so the MFJ is running, the cable is connected. We're going to start with the capacitance of the transmission line. So we press mode once, coax loss. Second time we've got capacitance in picofarad. So I'm gonna take whatever frequency. You can take whatever frequency. I just, for convenience, will round this number. Okay, so I will take whatever frequency and I will get this value, for example, 2000 picofarads. Okay, so I will register that at this frequency. This will be the capacitive reactance, 43, already calculated by the MFJ, but we're interested in C. So 2000 buff, okay, which is basically 2 nano, or if you want to express it in farad, will be 2 times 10 at minus 9 farad. Okay. We're gonna measure now the inductance. In order to do that, I'm gonna short the other end, and we just press mode again and read the inductance. Okay, the other end is shorted, and at the same frequency we measure 5.261 micro Henry, which means 5.261 time by 10 to the minus 6 Henry. We can enter those numbers in a calculator now and get the result. Okay, with the help of a calculator, I got the square root of the inductance in Henry divided by the capacitance in farads. So if we press equal for the results, we should get already the impedance in ohms. So I've got 51.2.3 basically, okay? So 51.3 ohms. This is the characteristic impedance. So let's have a look at a data sheet now for the characteristic impedance. Probably will be plus minus 2 ohms, something like that, but let's have a look. Okay, this is a data sheet of an RG213U, and as you can see in the electrical properties, I've got impedance 50 plus minus 2 ohm at 20 degrees Celsius. We've got 18 in here now, so we're pretty close. And our result was 51.3, so we are within the spec, I would say, within what we can expect for this type of cable. So I would say the first test is passed. Let's continue on with the second one. To measure the second, take the measurements on the second point, the inner and the outer conductor. Before we do that, I want to measure the length of the entire piece of coaxial cable. And in order to do that, we take again the MFJ and still connected, we switch it on. And we know that we take the menu number 2, and we know that the velocity factor for this cable is 66, as is shown there, but we can double check. So yeah, velocity ratio 66%. So we take that, both buttons, and we're going to measure the distance to full. Take the first measurement basically. Okay, so we look for the frequency where this needle goes down to the minimum, which corresponds to a electrical quarter wave. So I kind of interpolate because, as you can see, I have the 0 at 3.28, but I have 0 until 3.34 basically. So in interpolating, I will sit in the middle between 28 and 34. That will be 31. Okay, so I'll take the measurement here. This is to get the most accurate as accurate as possible measurement. Okay. Then I take the second measurement, which is where the cable will appear as a 3/4 wave. So we going to multiply this by 3, so we get near 10 megs basically. So we switch already. There you go, and we get the minimum here. So I got the one between 91 and I got a 0 here. Okay. Okay, so I can be pretty sure that I'll be in here basically about 20, 96, 97. Okay, get again, and we got the answer in feet. 48.7 feet. Okay, so what does it mean in meters? Let's take the calculator. 48.7 multiplied 3048 meters, which is 30.48 centimeters, which is the length of 1 foot. And we've got, let me see if I got it right, 48.7, yeah, 14.84 meters, 14 meters and 84 centimeters. Okay, so I'll take a note. I will take a note. The total length for 14 meters point 84, let's say 844. Okay. Okay, now let's measure the inner and the outer resistance with the help of a multimeter. Okay, let's start with relative measurements. We're gonna take out the because the value we're going to measure is quite low, so we take out the resistance of the wires, and now we measure the center conductor like this, and we measure 0.15. What is happening here? Probably a bit of oxidation, maybe. Let me check. Okay. Yeah, there's definitely a bit of oxidation in here, which makes sense because the wire has been this connector has been outside without protection for years, so I'm even surprised that it's still in these conditions. As you can see, the measurement is not consistent. The best thing to do would probably be to take the connectors out, because we want to measure the transmission line, not really the connectors. And after that, take the measurements. But yeah, it's the second time that I get this value 0.08. So it could be worse, but I mean, if I get 0.08, is already the best case. You know, it could be worse, but if I get this 0.08, it means that it's happening. Okay, so I will register 0.08. I will register that value, 0.08 ohms on the inner conductor. Now for the outer, it's probably better for me to take some spray for in order to assure the connection. For the outer conductor, the shielding, I asked the help of these two grubbers, and I'm measuring 0.12, 0.12, and let's take a note of that as well. Take this out and write down 0.12 ohm. Obviously, these values are both referred to this length, but the datasheet is giving us a number which is in a resistance in ohm per 100 meters. So let's do some math to express the same 400 meters, or you can do the other way around. Take the value given in the data sheet and transform it for this length. Either way. Well, actually, what we've got from the datasheet is the resistance in ohm per kilometer. Okay, so but it's easy math. Basically, 6 ohm per 1,000 meters would be 0.6 per 100 meters. Okay, so because we are talking 100 meters, my length here, my length is just an easy percentage of 100 meters. So it's basically 14.844%. So if we take 0.6 from the datasheet, 0.6 ohm per 100 meters, and we multiply that for this percentage, we can then compare the numbers. So 0.6 times 0.14844, which is 14%, okay, 14.844%. And we have 0.089. Let's write it down so you can understand. 0.14844% gives us 0.089 ohms. For my length, for this length here. Okay. We can do the same for the braid, which is 4.4 per kilometer, so 0.44 ohms per 100 meters times 14.844% gives us 0.065 ohms. Referred, sorry about that, it was out of the camera view, but here's the math, and yeah, basically we can now compare the numbers. So what I measured is in line with the data sheet for the inner conductor. I don't have the extra digit here. I don't know. Could be 1, could be 9. Most probably it's between 1 and 5. Otherwise, I would have 0.09. But anyway, it's also not a super precise measurement. For for the outer, I'm reading something which is in the range of double the resistance that we expect from the datasheet. So I'm going to check some other datasheet for the RG213. I don't know which brand is mine, because nothing is written on the coax. It's just lost from years of weather outside. But I'm going to have a look at a few brands and see what they report in order to get an idea of what would be, what it should be. And then probably my outer shielding is not in very good condition, especially because close to the connectors we got some oxidation. Better to cut out some pieces, take out the jacket, see if the conditions is good, and retake the measurement. I will definitely do that. But for now, this is the result, okay, for this second step. And we need to measure then the attenuation. Most probably will be higher than it should be, I guess. But let's have a look. Well, for the attenuation, we've got a function here which is called coax loss, which is pretty easy. You just take the frequency that you wish to measure and read the coax loss. The instrument is doing everything for you, is measuring basically the intensity of the response, the signal coming back, and is dividing it by 2. So we get the measurement of loss for this piece of coax cable. So the datasheet is giving us a reading at 5 megs. So if I take 5 megs, as you can see, I cannot measure less than, it's lower than 0.28 of a dB. So it's not of any help for us. So let's go up to the next measurement on the datasheet, which I have seen that is 10 megs. Okay, and I read, as you read as well, 0.3 of a dB at 10 megahertz. So once again, let's do some math. So once again here, we've got we have measured 0.3 for our length, 14-ish, 15-ish meters. I want to transform this in a 100-meter long cable as per datasheet. So it's just once again easy math. Basically, I'll do it again. You can write the proportion if you wish, and say that 0.3, 0.3 is proportional to 14.844, and is the same as saying that whatever attenuation is proportional to 100 meters instead. So you can just isolate x, just bring this 100 here, and this will become 0.3 times 100 is 30 divided by 14.844. And we can do it again. 30 divided by 14.844, and we've got 2.02 dB. 2.02, basically 2 dB. What is the data sheet saying for 5 megs, 10 megs, sorry? It's saying 1.8. So we have an extra 0.2 of loss per 100 meters. How much is it? 0.2 over 1.8 is basically 11.11%. Okay. Let's check at 50 megahertz. Let's check it again. So just grab the MFJ, which has gone in sleep mode. Meanwhile, press any button, go to 50 megs. Basically, as you can see, it's not critical. Let's see. We hit 1 at 57. We hit 0.9 at 49. So we are basically close to 0.9. Okay, it probably would be 0.91, something like that, but I cannot really tell. So I would say 0.9. 0.9. So at 50 megs, I measure 0.9 of a dB. With the same process, we can calculate that 100 divided 14.844 is our factor for our length, and then multiply for 0.9 we measured 6.063 dB. What should we get? 4.3. Okay, so it's getting worse. It's getting worse. So let me write down 6.06. Almost. If we want to bring it to 1 decimal only, I will write 6.1 dB of attenuation at 50 megahertz. So let's see. Next one is 100. Let's have a look at 100. One point three. 1.3. So 100 times 1.3 divided by 14.844. I got 8.76. 8.8 instead of 6.4. Okay, so I'll write it down here. 100, 8.8. So here was 11%. What about 50 megs? 6.1 instead of 4.3. It's definitely worse. 6.1 minus 4.3. 4.3. 1.8 is the difference over 4.3. Here it's gone 42%. What about 100 megs? 6.4 and 8.8. So that's difference of 2.4. 2.4 over 6.4 is 37. Yeah, probably. Obviously, you have to take account of the inaccuracies of these instruments. We can take other attenuation measurements with the help of some other instruments, and in fact I will do that as well, especially for higher frequencies. I think this one lacks of accuracy. So I got a couple of ideas to take some of the measurements, the same measurement for the attenuation at let's say 50 and 100 megs. I have this table written and ready to be filled in, and for measuring the attenuation I'll be using the power meter with the power sensor. This one is good for the range I want to measure, and an adapter in case I think I'll need it. And we will check the attenuation at 10, 50, 100, 200, and 400 as per this table from the datasheet of the coaxial cable. So I'll be generating a signal with the signal generator here at these various frequencies, and obviously I will measure the signal first, I'll zero in and do a relative measurement then. So after I take the measurement, I will get, well, first I'll connect the power sensor, take the measurement, zero the power meter, and then we measure. We insert the coaxial cable between the generator and the sensor at the end, and we check the dB difference. This one has a tracking gen, so it could be very useful to do this, but unfortunately it's not very calibrated. So it makes the life harder instead of easier. So I will just show one measurement, and then I'll repeat myself for the other frequencies, and then write down the table. Then we can compare that with the datasheet. The instruments have warmed up for a while now, so let's start the measurements. We are on 5 megahertz, the first frequency I want to test. The level is just choose arbitrarily 0 dBm, and we switch on the carrier and take the measurement on the power meter. So I read minus 0.18 dBm. So we zero that with the rel button, and now we can insert the coaxial cable and take the measurement again. Okay, I have connected now the coax cable in between. I have a couple of adapters, one in here from N male to SO239, and then there's the run of coax, and at the end I got the sensor connected, and another SO239 to N male to a double female N in order to connect to the N male of the sensor. And the signal is on, and we measure relative measurement of 0.22. So I'll build up a table now at all the frequencies and come up with the results. I have completed all the measurements and came up with this table. As you can see, the first column here is we've got the frequencies, and the first column is represented by all the values measured with the power sensor and the power meter from HP. Second column is the RG213, just for comparison and to see how it performs. And the last column is the calculated values from the datasheet for the 50 meters ish of length that I have, as the values are given, as you already know, per 100 meters. So first of all, we can see that the values measured with the MFJ are pretty close to the values those measured with the HP. So except that here I don't have the 200 megs with the MFJ, and the 400 was not reliable. So, but for these ones, the MFJ behaved quite well. So and then compared the values measured with the expected ones from the datasheet, and we can see here the delta attenuation on the different frequencies: 10, 50, 100, 200, 400, and as you can see, the difference is spreading out obviously, and reaching 1.26 of a dB, 1.26 dB for 400 megs. So I then draw this graph with frequencies on the horizontal axis and the attenuation values on the vertical one. The lower curve is the expected one from a good cable. The second one is the one that I measured for my cable. 400 megahertz would be down here, so but it gives us an idea anyway. This line is representing 2 meter band for 145 megs. I can see about 3 squares. That equals 0.2. Sorry, 0.2 times 3, 0.6 of dB, 0.6 dB, and in fact, we've got 0.47 at 100, 0.67 at 200, so in the middle is 0.57. So yeah, what can I say? Eventually, for this cable, for this piece of cable, I would use this cable probably up to 50 megahertz, not more than that. I don't want to lose already 0.6 dB. It's not that much, but I have other cables. I have an Ecoflex 10. I have other cables for HF. For HF, I will use probably a 5 or 7 millimeter. I have the Aircell 7, which is a good one and is also quite new, in good shape. So I will use that for HF, probably for the higher part of the HF. So maybe I will use this piece of coax for a 6 meter band when I will build and install a 6 meter Yagi. Where I just lose 0.3. So probably with the connections and another piece that I have in station, overall I will lose just 0.5, I guess, from the radio to the antenna. So yeah, that's all for now. So for these points here, we can say that the first one passed. The second one, we found that the outer shielding was showing a higher than expected, and that could probably be because of oxidation on the two ends. I will cut out some pieces and see if it improves. And so this is a kind of a partial pass. And attenuation, yeah, this is also partial pass. It's not even good or bad. Depends, as I said, where you want to use it. If you use it, for example, for HF, probably okay, I will use it for 6, as I said. So it's a partial pass. Probably going up higher in frequencies, it's a no, unless you want to lose some power there. But I don't want to. So that's my conclusion, and that's the end for this video. Thanks for watching this one as well, and I hope you found it useful, and see you in the next one. Bye bye, 7-3.